Okay, good morning, guys. Damodar, I saw your email. I'm sorry I haven't had a chance to reply. Yesterday I had a faculty senate meeting that ate up most of my afternoon. But I will have my normal office hours today if you want to come by and chat. If that doesn't work, we can set up another time in the next day or so.
Sure. I have physics when you have your office hours on Mondays and Wednesdays, so probably
Okay,
tomorrow
send
or
me
some
a
other
couple
time.
times that could work for you then. I have a doctor's appointment today around 5 that I have to go to, but as long as we're able to get together sometime today or early tomorrow, I think we should be able to sort things out. If it's urgent, we can try to squeeze you in between this class and my next class. But let me know when would work for you to meet.
It's not urgent. I'll just go to tomorrow's office hour.
Okay. So I have a few
Yeah.
cool things for you guys today. There's actually quite a bit to cover, so let's get to it. I don't know how many of you are actually in Gainesville right now, but it is fucking cold outside. First frost of the year. It's very nice. But yeah, today I'm going to start with a special treat related to power series. Then we're going to look at another polar graph, some more polar graphs. There's one or two examples that I really like to do that we haven't gotten to do yet. And then the last kind of big thing today is we're going to talk about how to find areas in polar coordinates, which is section 10.4. 10.4 actually talks about tangents and arc lengths as well as areas. But really the only problem that's made better in the polar coordinate system is the area problem. So we're just going to distill this down to the most beautiful and most necessary stuff. But I want to start with a special treat. So normally in Calc 2, I would do this through an activity where you guys get to discover this thing on your own. But all of the work we did with Power Series really deserves a payoff. You know, if you're going to put in a lot of work for something, you deserve to get something out of it. And you guys put in a tremendous amount of work this semester, especially with regard to infinite series, which is not easy stuff. So first, I just want to say how proud I am of you guys for hanging in there. This is a hard class. And I don't bullshit about this class. I really love this material, so I push you guys, and I'm really proud of you all for hanging in there and working as hard as you have. It's not a nothing thing to survive this class. So, take a second to be proud of yourselves and feel good about that. I am certainly proud of you. Here is our treat. There is a man named Leonard Euler. He went blind around the time of the American Revolution, around 1776. He was not an American. He was a Swiss, German, Austrian mathematician. Very, very smart man who lost his vision. His whole family is actually known for having vision problems. But if you look up a picture of him, um, there's a few different ways to spell his first name, but in English we would spell it Leonard. Leonard Euler. The last name here, Euler, is pronounced Euler. And it's actually after him that the number E is named. But he discovered something amazing. He discovered lots of amazing things. But perhaps the most amazing is that if you take the number E and you raise it to the power of I times theta, where I is what you think it is, the square root of -1, you get out the cosine of theta plus I times the sine of theta. And this is fucking bizarre. I just straight up, really, really weird. It's hard to figure out what it even means to raise a number to I times some other number. If you raise a number to the second power, that means multiply that number by itself. And you can kind of make sense of what it means to raise a number to a fraction power by thinking about roots. So you know the 3/2 power, you take the square root and then cube it. So you take the square root and then multiply that by itself 3 times. But what does it even mean to say I'm going to take a number and raise it to the 2i, or raise it to the 3i, or pi I? Those are mighty weird concepts, but it turns out the right way to interpret this stuff is using power series. And this started a whole field of mathematics called complex analysis. So I'm going to prove this for you. I'm going to prove to you that e to the I theta is cosine theta plus I sine theta. And then we're going to look at some really shocking consequences. We need to begin with 3 power series. E to the x, that's sigma n from 0 to infinity, x to the n over n factorial, which is 1 plus x squared over 2 plus x cubed over 3 factorial plus x plus x to the 4 over 4 factorial plus x to the 5 over 5 factorial, and so on. Cosine of x is sigma n from 0 to infinity, negative 1 to the n over 2n factorial x to the 2n, which is 1 minus x squared over 2 plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, and so on. And sine x, which is sigma n from 0 to infinity, negative 1 to the n over 2n plus 1 factorial times x to the 2n plus 1, which is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and so on. The other thing we need to do is look at powers of I. So I to the 0, anything to the 0 is 1. I to the 1, well, that's just I. I squared is negative 1 because I is the square root of negative 1. I cubed is I times I squared. I squared is negative 1, so this is negative 1 times I, or just negative I. And I to the 4 is I squared times I squared, which is negative 1 times negative 1, which is positive 1. And they loop after this. I to the 5 is the same as I to the 1. I to the 6 is the same as I to the 2, and so on. So I to the 5 is the same as I to the 6 is I cubed times I cubed. How else would you think of this? It's the same as I squared, yeah. So this would be negative 1, and so on. So I'm going to use these 2 sets of facts, that these power series are what they are, and that powers of I do this, to find a power series for e to the I theta. And then I'm going to split that into 2 series, and you'll see one of them is cosine, the other one is sine. I'll split them according to whether they have i's or not. So here goes. Here's the proof of this really wild statement. So e to the I theta, I'm going to take the series for e to the x and just plug in I theta for x. So this is the sum from n equals 0 to infinity. I theta to the n over n factorial. right? Just everywhere there's an x here, I write I times theta instead. It is just like some of your homework problems where you had to find a series for 1 over the 10th root of e or something like that. Now I'll start writing the terms of this series out. This is I theta to the 0 over 0 factorial plus I theta to the 1 over 1 factorial plus I theta to the 2 over 2 factorial. And I'm just going to give myself a bunch of terms here. I theta cubed over 3 factorial plus I theta to the 4 over 4 factorial plus I theta to the 5 over 5 factorial plus I theta to the 6 over 6 factorial. One more, we'll do I theta to the 7 over 7 factorial, and so on. Anything to the 0 power is 1, so this is 1 plus, this is I to the 1 theta to the 1 over 1 factorial plus, this is I squared theta squared over 2 factorial plus, this is I cubed theta cubed over 3 factorial, and we go on like that. I to the 4 theta to the 4 over 4 factorial, I to the 5 theta to the 5 over 5 factorial, I to the 6 theta to the 6 over 6 factorial, I to the 7 theta to the 7 over 7 factorial, and so on. And here's where I make use of my facts about powers of I. 1 plus I theta, nothing I can really do there. I squared, though, that's -1. So this is minus theta squared over 2 factorial. I cubed is -I, so this is minus I times theta cubed over 3 factorial. I to the 4, what was that? Well, I to the 4 is I squared times I squared. That's -1 times -1, so this is just +1. So this is plus theta to the 4 over 4 factorial. I to the 5, now we're looping. I to the 5 is just I, so this is plus I times theta to the 5 over 5 factorial. I to the 6 is -1, so this is minus, oh wait, is it minus I? Let me think for a second. That's I times I. No, it's -1. Yeah, minus theta to the 6 over 6 factorial. And then I to the 7 is minus I. So I should really write this minus I theta to the 7 over 7 factorial, and so on. Now, if you come in here and look at the guys that don't have i's, this one, this one, this one, and this one, they don't have i's. So let me group them together. This is 1 minus theta squared over 2 factorial plus theta to the 4 over 4 factorial minus theta to the 6 over 6 factorial, and so on. And I'll put him in some params. I'm going to split that series up. And now from the rest of these that do have i's, I will factor out the I. So I have plus I times, and then what's left here is theta minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial minus theta to the 7 over 7 factorial, and so on. And now I ask, do you recognize those power series? Cos x is this. So this is cos theta. Sine x is this. So this is sine theta, which means what we have altogether here is cos theta plus I times sine theta. So e to the I theta really is cos theta plus I times sine theta, and that's the proof. There's really no nice way to prove this besides using power series. That's one of the reasons why it's so neat to do this here. Because before this class, there was no way you guys could have done this. And it's kind of shocking. It might not be obvious yet just how shocking this is, so I'm going to show you a few special cases. First, remember e to the x, that's not a bounded function. E to the x normally grows, gets really, really big. But sine and cosine are both bounded, right, between -1 and 1. So somehow plugging the I in here makes this a bounded function. Weird. E to the x is monotone, always increasing, but neither of these are monotone functions, so that's a little bit weird. E to the x is always positive, but neither of these are always positive, so that's a little weird. One of the most famous consequences of this, which is called Euler's identity, if we plug theta equals pi, so you may have noticed throughout the semester, a few days, I wore a shirt that said something about e to the I pi. Well, e to the I pi, according to this result, should be the cosine of pi plus I times the sine of pi. The sine of pi is 0, and the cosine of pi is -1. So it says e to the I pi equals -1. And another way to say that is e to the I pi plus 1 equals 0. And if you've been paying attention in your pre-calculus and Calc 1 and hopefully Calc 2 class, this should be really shocking. This breaks all the rules. The exponential function is not ever supposed to be negative, but here it is outputting a negative number. Mathematicians and people who like to talk about mathematics often refer to this as something very beautiful because it involves all the special constants, e, I, pi, 1, and 0. And it also involves all the special operations, equality, addition, multiplication, and exponentiation. So there's something very, very beautiful about this. There's something that is very aesthetically pleasing to a mathematician about this statement. And it's utterly shocking, really. Should not be true. The first time I saw this, I didn't believe it. My Calc 2 teacher showed me, and I said, no. It just doesn't make sense. It's just not possible. But it is. Another kind of funny thing, you may have heard that you can't take the natural log of a negative number, right? The natural log's domain is just 0 to infinity. So natural log of -1 doesn't exist. It doesn't even make sense to ask what it is. I claim that that's not true if you're willing to work with complex numbers. So take this expression right here. And take the natural log on both sides. The right-hand side is the natural log of -1, which is this thing that's not supposed to exist. The left-hand side is the natural log of e raised to some stuff. Well, if you raise e to any power and then take the natural log, you should just get that power. So the natural log of -1 does exist. It's just not a real number. So here's a kind of shocking fact number 2. That is a consequence of this theorem. Natural log of -1 does exist. It's just not a real number. It's the complex number I pi. What else can we do? Well, one of my favorite things here. So we know what I is. What happens if you take I and you raise it to the power of I? This is, again, one of those things that's hard to make sense of. What does it even mean? I'm going to multiply I by itself, I times. Well, I isn't a counting number, so I have no idea what that means. But there's a way to make sense of it here. And the way this is usually phrased is, do you think this is a real number or not? All right, you've got a complex number raised to a complex number. Do you think that's going to come out to be a real number? Most people would say, nah, probably not a real number, right? Complex number raised to another complex number. Well, you can attack this using Euler's result. You just have to recall that a to the b, that should be the same as e raised to the natural log of a to the b. All right, because e raised to the log of anything is just that thing. And then by properties of logarithms, this b can come down in front of the logs. This is e to the b times the natural log of a. So I to the I is e to the I times the natural log of I. And we can figure out the natural log of I by thinking e to the I theta is cos theta plus I sine theta, and plugging theta equals pi over 2. So if I plug theta equals pi over 2 here, I get e to the I pi over 2 equals cos of pi over 2, which is 0, plus I times the sine of pi over 2. Sine of pi over 2 is 1. So in other words, what we have here is that e to the I pi over 2 is equal to I. And now if you take natural logs, you get that I pi over 2 is the natural log of I. So let's come back to this now. Therefore, I to the I, which is e to the I times the natural log of I, should be e to the I times, well, the natural log of I is I pi over 2. And I times I is -1, so this is e to the negative pi over 2. I to the I is in fact a real number. It's e to the negative pi over 2. So these are just a few of the really surprising things that show up as a consequence of Euler's identity. E to the I theta equals cos theta plus I sine theta. Very, very weird stuff. It allows us to take the natural log of negative numbers. It allows us to take the natural log of complex numbers like I. It allows us to do all sorts of things that you would have never thought viable. And Euler didn't have anybody before him to tell him anything about this shit. He discovered it all fresh himself, blind. Remember? Blind. So Euler just laid down on his couch and he would dictate mathematics to someone who would sit there and write it down. And this is one of the things he discovered. Many, many other things he discovered also, made all the more amazing by the fact that the man had no sight. He was totally blind by 1776. So there's a lot of cute sayings about Euler. My favorite comes from Richard Dedekind. Just said, read Euler, read Euler. He is the master of us all. And he's 100% right. Euler was a genius unparalleled in his own time or since. And this stuff, this e to the I theta is cos theta plus I sine theta, is hugely important in nearly every field of mathematics and physics, especially if you're interested in electrodynamics at all. So quantum physics or circuit design, anything like that. Really, really beautiful stuff. And I invite you to play around with that. You know, Google it, do whatever you want to do. If this feels weird to you, that's a good intuition. This should feel very weird because it is very weird. And if you want to explore the different ways that this weirdness can be important or interesting, I invite you to do so. There's lots of beautiful things you can do.
Are we going to have questions similar to this on the exam?
God, no. No, this is just a little fun treat. So this was our payoff for doing all the power series work. I would never ask you questions on an exam like this. So I guess we should get back to the stuff that's relevant to the class. There's two other things I wanted to do with you guys today, and that was to show you a few more polar graphs and also show you how to calculate areas in polar coordinates. All right, so let's move on to that second item. Okay, so that was the fun stuff. Now we have to get back to the work. I just want to work through a couple more examples with you guys. So one example that's worth going through here, a family of examples really, are functions that look like this. All right, so I want to graph in polar coordinates r equals sine 2 theta, 3 theta, 4 theta, stuff like that. Cosine 2 theta, 3 theta, 4 theta. I should get comfortable with all those. Remember, the trick is to first graph in Cartesian coordinates. Recall that the period of sine AX or cos AX is 2 pi over A. So this guy has period 2 pi over 2, which is pi. We always need to graph at least out to 2 pi, so we know what happens as you revolve all the way around the circle in polar coordinates. That means I'm going to go through 2 full periods of this function from 0 to 2 pi. So I'll mark this as 2 pi, which makes this pi. Here's pi over 2, which means this is pi over 4, 3 pi over 4. This is 3 pi over 2. So this is 5 pi over 4 and 7 pi over 4. So I've got one full period between 0 and pi. So I know I'll be all the way back here. So by the time we're at pi over 4, you should be up to 1. Back to 0 by pi over 2 and down to -1 by 3 pi over 4. So my first period of this wave looks like this. And then we have another full period between pi and 2 pi. So graphing sine 2 theta in the normal rectangular coordinate system looks like this. Then if I want to get the polar graph, I have to imagine that kind of revolving arm. All right, I imagine a little arm that like revolves around, and there's a guy running in and out on that arm according to this pattern. I'm going to give myself some helper lines here. So like here's theta equals pi over 4. Over here would be theta equals 3 pi over 4. Down here would be theta equals 5 pi over 4. And over here would be theta equals 7 pi over 4. And as you work through these problems in your homework, again, I want to encourage you to look at some polar graphing paper. Maybe print some polar graphing paper. It's online all over the place for free. You can download a PDF and print it out. I want to take this graph and translate it into polar coordinates one little chunk at a time. The largest r ever gets is +1. So I'll go ahead and come out here and mark this as +1. Kind of set my scale. When theta is 0, r is 0. If my little arm hasn't started to rotate at all, then r is 0. So I'm still back there at the origin. But as I start to rotate, r is going to start to grow. And it's going to grow out to a max of 1 at pi over 4. So if you imagine rotating just a little bit, my arm rotates just a tiny little bit, then r should have come out just a tiny little bit. So if I rotate up a little bit, we should come out a little bit. If I rotate up a little bit more, we should have come out a little bit more. And if I keep this pattern up, I should get all the way out to this guy, whose polar point is 1, pi over 4. So I get a shape that looks like this. As my arm rotates past pi over 4, just a little bit past, r should start to come in. So if I rotate just a little bit past pi over 4, instead of still being out here, I should have come in a little bit. So we will be like here. And then if I rotate a little bit further, r should come in a little bit further. So I'll be like here. And by the time I get to straight up and down at pi over 2, r should be 0 again. So we're going to come back into the origin along these dots. So that will draw something looking like this. So this loop of the curve here is coming from this part of the Cartesian graph. As theta goes from 0 to pi over 2, you imagine this arm rotating around and watch where the arm intersects. R is getting bigger and bigger and bigger and bigger and bigger and bigger and bigger out to a max of 1. And then r starts coming in, getting smaller and smaller and smaller and smaller and smaller, all the way back to the origin by the time this rotates up to pi over 2. As we rotate past pi over 2, say from pi over 2 to 3 pi over 4, normally I would be drawing in quadrant 2 over there, right? From theta equals pi over 2 to theta equals 3 pi over 4. But r here is negative, right? These are negative r values. So rather than drawing in this region, I'll actually be drawing in the reflected region over here. Remember, when r is negative, your points are reflected through the origin. So based on this shape, I would expect to draw something like this. But instead, I'll be drawing in this reflected region over here, something like this. It can help to plot a few points. So one of the points I know for sure is going to be on the graph. This is 3 pi over 4. Is theta equals 3 pi over 4, but r is -1. So that's going to be over here. I have this point, which is -1, 3 pi over 4. And the shape is going to be similar to the one we just drew. Now, something that can be very useful is to come in here and like shade or color a portion of this graph to remind yourself which part of the polar graph came from which part of the Cartesian graph, because it's not obvious that the part I'm coloring blue right now if you're just looking at the polar graph, you would think that this is coming from the theta values 3 pi over 2 to 7 pi over 4, because it's over here in quadrant 4. But really it's coming from pi over 2 to 3 pi over 4. It's just been reflected over here because r is negative. So as we rotate through here, r is negative, so I'm doing the same thing, but I'm drawing in this reflected quadrant. And now here is my arm at 3 pi over 4. We would have expected to be drawing over here, but because r is negative, we have to reflect all that stuff, and we end up drawing over here. Now, as I rotate past 3 pi over 4 towards pi, I would expect to be drawing over here, but from 3 pi over 4 to pi, r is still negative, so I'm still drawing in this region. And the same sort of thing is happening. As I go from 3 pi over 4 to pi, r is tucking back into 0. So I end up drawing something that looks like this. All right, so we are here at theta equals pi. If I let this continue to rotate from pi to 5 pi over 4, I expect to be drawing in quadrant 3 down there. And thankfully, r is positive from pi to 5 pi over 4. This is pi to 5 pi over 4. So I will be drawing in the region we expect, and I'll reach r as a max of 1 when theta is 5 pi over 4. So here's this polar point 1 comma 5 pi over 4. And from theta equals pi to 5 pi over 4, I will draw something like this. And then as theta advances from 5 pi over 4 to 3 pi over 2, that's rotating from here to here, r comes back in. We're going from r equals 1 back to r equals 0 as theta rotates from 5 pi over 4 to 3 pi over 2. So we're going to tuck back into the origin. And this time we're coming in, that's corresponding to this point right here. And then we've got another little bloop here where r is negative. So as theta goes from 3 pi over 2 to 2 pi, normally I would expect that to mean drawing down here in quadrant 4, 3 pi over 2 to 2 pi. But since r is negative, I'll really be drawing in the reflected region up here in quadrant 2. And the symmetry of the Cartesian graph, the symmetry here, you can kind of guess that this is going to be, here's my polar point, -1 comma 7 pi over 4, that's this point. We'll end up drawing something like this. And then here is us coming back in when theta is 2 pi. So these are called rose graphs or petal graphs. One of the things I'm going to show you how to do today is find the area enclosed by this loop. It's not what you would think. You might think that this area is the same as this area, because this petal is coming from this little hill on the Cartesian graph. But the geometry is such that they don't come out the same. They're different areas. So I'll have to show you how to find this area. It requires cooking up its own little Riemann something and then its own little integral formula, just like the last few applications we've seen. But before I do that, I wanted to show you a few more graphs like this to help you get a feel for what they look like. And we don't have time to do a bunch of them by hand, but I can show you in Desmos. So. Let's go into polar mode. Here's the graph we just drew. And it looks how we thought it would look. What happens, do you think, if I change this 2 to a 3? So sine 2 theta has 4 petals. What do you think sine 3 theta would have? Yeah.
6?
Yeah, that's a very reasonable guess. But it's got 3. So there's something interesting going on here. Sine 4 theta will have 8. Sine 5 theta will have 5. Sine 6 theta will have 12. Sine 7 theta will have 7. So it depends on whether this number is even or odd. If the number in here, by the way, is called angular velocity. It's the angular velocity for this function. If the angular velocity, the constant in front of the theta inside of sine, is odd, then you'll have that number of petals. If it's even, you'll have double that number of petals. It's because when this is odd, you end up tracing each petal twice. But when this is even, the geometry works out such that you trace each of these only once. Another fun question is, what happens if I change the sine to a cosine? Well, here's
I can't see your screen. I don't know if it's like not screen sharing.
It says it's screen sharing. I'll turn it off and turn it back on again. Is that better?
Yeah.
All right, let's run through that one more time then. Here's the thing we just graphed. And if the number inside here is even, you'll have twice that number of petals. So sine 2 theta has 4 petals. Sine 4 theta has 8. Sine 6 theta has 12. Sine 8 theta has 16. But if the number inside is odd, you'll just have exactly that number of petals. Sine 3 theta has 3. Sine 5 theta has 5. Sine 7 theta has 7. So the other fun question is, what happens if I change the sines to cosines? It just kind of rotated a little bit, didn't it? Right? The blue is the sine, the red is the cosine. It's actually a 90-degree rotation. It's a rotation by pi over 2, but it's not super obvious that that's what it is. It looks like it's just a slight shift. One way to think about this is that cosines will always start out at their max, and sines always start out at 0. But here's cos 7 theta. Let's look at cos 2 theta. You can compare this to the one we just drew. Sine, cosine. Same shape, just out of phase. And the rule that I described for the sines works just as well for cosines. If the number is even, you'll have twice that many petals. If the number inside is odd, you'll have exactly that number of petals. So these are called rose graphs or petal graphs. And they're neat things. They're not that hard. You should practice drawing a few of them by hand, going through this exact process. On the final exam, I will ask you to do this. I'll give you something like sine 2 theta, r equals sine 2 theta, and I'll tell you, give me the Cartesian graph. You need to graph it out to 2 pi, from 0 to 2 pi, and then translate that into a polar graph. And then I might ask you to do something with this polar graph, like maybe tell me which portion of the Cartesian graph did this petal come from, or set up an integral that represents the area of this petal. And the next thing I want to show you is how to do that integral, how to set up that integral. So
For this next exam, what will we need to know from like polar coordinates?
just up to the converting a point from polar to Cartesian or Cartesian to polar.
Okay.
So on exam 3, I won't ask you to do any function graphing, and I won't ask you to do any area work because you won't really have time to practice that between now and Friday. But I will ask you to do the stuff that I showed you on Monday. So like, here's a polar point, give me the Cartesian coordinates. Here's a Cartesian point, give me 3 polar coordinates that get you to that same point. So just the stuff that we did last time. Now let's talk about areas. My art skills are a little bit limited here, but there's some things we need to talk about first, so I'll show you those. Remember that when we wanted to find areas in rectangular coordinates back at the end of Calc 1, you approximated your functions by constant functions, right? That's where your rectangles came from. Your rectangles are each like constant functions. The constant functions in the polar setting here are circles, right? R equals 1, R equals 2, R equals 3, R equals 4. Those are circles centered at the origin of radius 1, 2, 4, whatever. So one thing we need to know before we can dive in here is the area of a sector of a circle. So if I have a circle and I ask for the area of just a piece of that circle, maybe this piece, what is that area? That's definitely going to depend on the radius. That's sweet, but yeah, drawing circles is tough. It's harder than it seems. So if this is a circle of radius r, you know that the total area of the circle is pi times r squared, right? We all remember that. Area of a circle is pi r squared. The area of a sector should be related to the area of the total circle, right? Whatever formula I have for the area of this sector should give me the area of the whole circle when I plug in theta equals 2 pi. And if I plugged in theta equals pi, it should give me half the area of the circle. When I plug in theta equals 0, it should give me 0. It should be the unique linear function that is equal to this when theta is equal to 2 pi. So the area of a sector is A equals 1/2 theta r squared. You can try this. If you plug in 2 pi for theta, then the 2 cancels with the 1/2 and you get pi r squared. If you plug in pi for theta, then you get 1/2 pi r squared, which is definitely half the area of the circle. And if you plug in 0 for theta, you get 0. This makes sense. This is the unique linear function of theta that agrees with this guy at 2 pi. So your constant functions in Cartesian coordinates are horizontal lines. Your constant functions in polar coordinates are concentric circles. The trick to figuring out areas in polar coordinates is to approximate by the appropriate constant function. Now I'm going to show you this in the book and then I'll do my best to draw it. Here's the idea. If r is a function of theta and you want to find the area bounded from theta equals some number to theta equals some other number, right, this blue shaded region here, the trick is to chop that up into a bunch of little things, and then each of those little things you approximate by thinking of them as areas of sectors of circles. I forget whether your book does sectors or triangles. Both work. Smaller region, central angle. No, yeah, they do sectors. All right, so I'm going to do my best to draw this for you in a way that makes it palatable. So how to find area bounded by r equals, I'll use r of theta for my function here. That's the more sensible notation. From theta equals a to theta equals b. All right, so this is going to be my polar graph. And let's just suppose it looks like this, right? Whatever, you know, could look like something else. Here's my polar axis. So here's the function r of theta. I want to find the area from this angle to this angle. So here's A, and this guy here is B. I want to find the area of this region, right? The region enclosed here. The trick is to chop it up into a bunch of little areas. Each one I approximate by a constant function. So I'll chop this up into a bunch of pieces. Something like this. This is where my art skills really get put to the test. Big fat points. Eh. Okay, something like this. And then in each of these regions, I'm going to think of this function as being a constant function, meaning like a circle. Like this. That's the idea. So I chop the theta interval AB into n equal length subintervals. Each of width delta theta, which is b minus a over n. So like this little angle in here is delta theta. 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 This little angle in here is delta theta, and delta theta. That's the idea. And then each one of these little wedges I can think of as being an area of a sector of a circle. It's an approximation. It's not exact, right? You see, like, for instance, here, I'm way overshooting. For here, I'm overshooting a little bit. Here, I overshoot and undershoot a little bit. But it's just like a Riemann thing. It's just that instead of having Riemann rectangles, you have Riemann wedges now. The polar coordinates for the point down here, it's always r comma theta. So this is r of a comma a. This would be r of, I'll call it theta 1, comma theta 1. This would be r of theta 2, comma theta 2, and so on. And each of the little areas I'll call A1. Oh wait, no, that's not one of mine. A1, A2, A3, A4, and so on. So my total area A is approximately the sum of the AIs, sum from I equals 1 to n AI. And each AI is a sector. Each AI is a sector of a circle, so it's 1/2 the angle inside, which is delta theta for all of them, times the radius. And each one of these has radius r of theta I times that radius squared. So I'm using my formula for the area of a sector of a circle, 1/2 theta times r squared, where the internal angle for each of these is delta theta, and the radius for each of these is r of theta, like r of theta 1, r of theta 2, and so on. So this area can be written as sigma I from 1 to n 1/2, I'm going to write the r of theta squared first, r of theta I squared times delta theta, which is a Riemann sum for a certain integral. So now as I send n to infinity, which is a Riemann sum for the integral, and this is the exact value of that area. Now a is the integral from little a to little b, 1/2 r of theta squared d theta. And that's it. That is your exact area. So if you want to find the area enclosed by a polar curve between theta equals a and theta equals b, you don't integrate your function. You integrate 1/2 times the square of your function, which is strange, but it's just how the geometry works out. Cool shit, right? So let's take this and come back to this guy. Maybe I want to find the area of that first loop. This was sine 2 theta. I need to figure out what angles correspond to this loop. So this loop started when theta was 0, and it finished at theta equals pi over 2. And then I integrate 1/2 times r of theta all squared. Well, that's sine squared 2 theta d theta. And that's all. This is how this is done. So you integrate not your function, but the square of your function. And then you multiply by 1/2. That will give you the area enclosed by that polar curve. We can crunch this out. The 1/2 can pop out. I have integral 0 to pi over 2 sine squared of 2 theta d theta. Does anybody remember how to integrate sine squared? How do we do this?
You use the identity.
Yeah, which identity?
1/2 parentheses 1 minus cosine of 2 theta.
Good. Yeah, so there's this pair of identities. I always remember them together. Cos squared x is 1/2 1 plus cos 2x. And sine squared x is 1/2 1 minus cos 2x. So I'll use this identity here. The catch is that instead of an x inside, I've got a 2 theta. So this will be 1/2 integral 0 to pi over 2, 1/2 times 1 minus the cosine of 4 theta, 2 times 2 theta, like that. I can pop the 1/2 out. It'll join its buddy to make a 1/4. And then I'm left with the integral from 0 to pi over 2 of just 1 minus cos 4 theta. An antiderivative for which is not hard to find. So this is going to be 1/4 times theta minus sine 4 theta over 4, evaluated from 0 to pi over 2. If I plug in 0, I get 0 minus the sine of 0 over 4. That's definitely 0. If I plug in pi over 2, though, I get 1/4 times pi over 2 minus the sine of 4 times pi over 2 all over 4. This is the sine of 2 pi, which is 0. So this is really just 1/4 times pi over 4 is pi over 8. So that's the area of that loop, is pi over 8. And areas of other polar curves come similarly. There's nothing really special here. So these are not challenging problems except for one thing. I want you to imagine that I asked you to tell me an integral for this guy. You might say it's the same integral, we just go from 3 pi over 2 to 2 pi. That's what it looks like, isn't it? But remember where this guy came from. He actually came from not 3 pi over 2 to 2 pi. He came from pi over 2 to pi, because r was negative there. So this is why I shaded this piece as we did it, so we could remember that this is not coming from the region it looks like, from 3 pi over 2 to 2 pi. It's actually reflected and coming from pi over 2 to pi. So if I asked you for an integral representing the area of this loop, you would tell me that it's the integral from pi over 2 to pi of 1/2 r squared. That's the only thing that can be tricky about these, is figuring out what theta values correspond to which part of your polar curve. Now, if you draw your polar curve by hand, you'll remember. But if you hack it by looking at a graphing utility, you'll get it wrong. So you need to practice drawing these polar curves by hand. That is necessary. It's the last big skill I need you guys to practice for this class. If you don't want to grind on it right now, that's okay, because exam 3 isn't going to have this on it. This will only show on the final. But you need to practice it before the final, because the final, like I said, will have a problem where I ask you to draw the Cartesian graph, then draw the polar graph, and then I might ask you for an integral representing a loop like this or something along those lines.
How many questions are on the final exam? Or like roughly?
About 20. Yeah, it'll be about a third longer than a regular test.
Okay. And for this third exam, I just wanted to kind of go over like what specifically we need to know from each section, because I know some of it's more like not related to this exam.
Yeah, let's go ahead and have a list of topics for exam 3. So again, exam 3 is this Friday during class time. So the sections covered are 11.8, which was the Intro to Power series. So this is like the definition, the radius and interval of convergence. So I could ask you, for the radius or interval of convergence of a power series, or I could give you some of those tricky problems where I say this power series converges when you plug in 5. Can you tell me if it converges when I plug in -3? That sort of thing. 11.9, this was on representing functions as power series. And this was before we had Taylor's theorem. So this was using the geometric series trick. And also integrating and differentiating power series. So that's stuff like where we found the series for the natural log of 1 plus x by integrating the series for 1 over 1 plus x, or found a series for 1 over 1 minus x all squared by differentiating the series for 1 over 1 minus x. The next topic in section there was 11.10. This was Taylor's theorem. That's where you cooked up the series for e to the x, sine x, and cosine x by using the tables, right? And I could ask you to cook up a series for any other function using one of those tables. Or at the very least, I could ask you for like the first 5 terms of the series. So you'd have to fill out that table to n equals 5 and then write out the first 5 terms of the series, that sort of thing. This was working with the table. That table had n, fn x, fn of a, and cn table. And then we jumped to chapter 8. 8.1 was on arc length. 8.2 was on surface area. And this is going to be the bulk of exam 3. There will also be some stuff from 10.1, which was on parametric curves. So graphing a set of parametric equations. And also finding a parametrization. So maybe I could give you a graph and say, find some parametric equations that have this graph as their graph. 10.2. Here we talked about tangents and arc length for parametric curves. And then 10.3 was polar coordinates. Ten point 4 we covered today, which is areas in polar coordinates. These guys will be very gentle on this test. So the stars here, very little. On exam 3, more on the final. Specifically, the things that I could ask you to do from those sections on exam 3, tangents and arc lengths of parametric curves. I could ask you to find the horizontal or vertical tangents. I could ask you to set up an integral for an arc length, but really here I wouldn't expect much of anything from this on exam 3. This will mostly be on the final. Polar coordinates, the only thing I would really ask you to do here is convert a point from polar to Cartesian, or from Cartesian back to polar. I won't ask you to graph anything on exam 3, and I won't ask you to find any areas on exam 3. These will just be so these two, 10.4 and 10.2, will really just be on the final. 10.3 will show up on exam 3, but only in the gentlest of ways, like asking you to convert a point back and forth from polar to Cartesian. Okay. Any other questions here? Anything else that we're dying to know before, how am I doing on time? Oh yeah, we got about 4 minutes left.
Along with like the office hours available today and tomorrow, are you doing any office hours over the weekend for like any questions related to the final?
Yeah, I will add at least 1 office hour over the weekend to help prep for the final. So I've got it won't just be a Calc 2 office hour. but I will have at least one office hour over the weekend for people who have questions regarding the final, probably Sunday. All right, anything else I can help with here? Any problems that we would like to see an example of in these last few minutes? Eddie, sounds like you got a lot of white noise in the background there. If there's something you wanted to say, try typing it in chat.
Hello.
Hey,
I wanted to see a question from the homework.
yeah. Which one? From homework 13? Or from
Yeah,
study
the
guide?
last one.
Okay, which one would you like to see?
Number 20.
Oh, okay, yeah, the very last problem here. So this is a cool problem. We want to find the length of the loop of this curve. So I recommend looking at this in Desmos. If you try to plot this by hand, you can do it, but it's going to take a while. So for the sake of time here, I'll graph this in Desmos. We had 12t, what is it? 12t minus 4t cubed, that's our x function. Comma 12t squared. Oh, and I'm still in polar form, aren't I? Yeah, let's get out of this. Back to this. And let's let t run from like -5 to 5. And let's zoom out. Zoom way out. Okay. So here's what this curve looks like. The loop here is this piece, right? So we want the arc length of that loop. So I need to figure out what t values correspond to the start of that loop and the end of that loop. Just for fun here. Will it give me the option to add a slider? Yeah, let's do that. 4. Wait, let me do it a little differently here. Let's do S cubed. Yeah, so add the slider. S squared. Okay, so here you see this thing, this particle moving around along this graph. I'd like to find out what time values, what correspond to the start and end of that loop. And if you zoom in and look close here, you'll see that this is like halfway between 30 and 40. It's actually 36 if you zoom in a little further. So I want to figure out where's the y function, which is 12t squared. Where is that equal to 36? That'll give me the t values I need. So let me swap back to my .cam and we can go through this. We need to find the length of the loop. And x of t equals 12t minus 4t cubed. Y of t equals 12t squared. And we saw that the loop starts and ends at the point 0, 36. So we can find the t values by solving y of t equals 36. That's the same as saying 12t squared equals 36, which is the same as saying t squared equals 3. So t here is plus and minus the square root of 3. So that loop begins when t is equal to negative root 3, and then it ends when t is equal to positive root 3.
So is graphing it the only way that you could find that second point that completes the loop?
Yes, you would either need to graph it by hand by plotting points, which is very doable, right? If you just plug in like t equals -2, -2, -1, 0, 1, 2, you'll find that loop, and then you would discover that this point is the point where the loop starts and ends, and then you would need to solve this equation to find the t values. You'll never guess these t values, but you can sketch the graph either by plotting points by hand or by using Desmos. Either one would be okay here. And then you'll solve this equation to find the t values. So our arc length is going to be the integral from -√3 to +√3 square root of dy dt squared plus dx dt squared. And that integral is, of course, done dt. So dy dt and dx dt. Dy dt is 24t. Dx dt is 12 minus 12t squared. So this is going to be integral -√3 to +√3 square root of 24t all squared plus 12 minus 12t squared dt. And the first thing I see here is that all of these pieces are divisible by 12. So this is square root of, I'll write it like this, 12 times 2t squared plus 12 times 1 minus t squared squared. So you can square the 12s. This is 144 times, left there is a 2t squared plus 144 times 1 minus t squared squared. And then I can factor the 144 under the square root and bring it out as a 12. So I'll get 12 integral -√3 to +√3 square root of 2t squared, that's 4t squared, plus, and then here I'll have 1 minus t squared. I'll just leave it like that for now. So we comfy up to here? My next step is going to be to FOIL this out. So under my square root, I'll have 4t squared plus 1 minus 2t squared plus t to the 4. And then I can combine the like terms, 4t squared and minus 2t squared. So that looks like 1 plus 2t squared plus t to the 4 under my square root. Now I can't give the square root to each of these pieces on their own. That does not work, never works. Square roots do not play nice with this addition. But if I could factor the thing under the square root, that might help. Does anybody see a way I can factor the radicand here?
t squared plus 1.
Yeah, remember that a plus b all squared is a squared plus 2ab plus b squared. So this is 12 integral negative root 3 to positive root 3 square root of 1 plus t squared squared. And that's our saving grace here, because now this outer square and this square root will cancel. So I end up with 12 integral negative root 3 to root 3, just 1 plus t squared dt. And now this is an even function. So if I want to, I can call that 24 integral 0 to root 3, 1 plus t squared. And from here, things are easy. So I'm using the fact that, if you integrate an even function from negative a to a, that's the same as integrating the double of that from 0 to a. And the antiderivative here is t plus t cubed over 3. And I evaluate that from 0 to root 3. At the lower bound here, I clearly get 0. At the upper bound, I get 24 times the square root of 3 plus the square root of 3 cubed over 3. And the square root of 3 cubed is 3 root 3. So this is 24 times root 3 plus 3 root 3 over 3. You can cancel the 3's. And you get 24 times root 3 plus root 3. That's 48 square roots of 3. So the trick here is getting the graph first. All right, you got to get the graph. I'm okay with you using Desmos, but I want to make sure that at least for a handful of these problems, you draw them by hand. So my preference here would be that you sketch this curve by hand and then verify with Desmos. If you plug in like t equals -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, you will absolutely get this picture. You'll have no problem drawing this by hand. Then you can look in Desmos and verify that that's the case, and you'll see that the loop is right here. So once you've got that, you just need to figure out the t values that correspond to the start of the loop and the end of the loop. And if you watch this point come in, here it starts, ends. It starts and ends at this same point up here, which is 0, 36. So you plug in 36 for y, you set 12t squared equal to 36, and that will give you your two t values, which were plus and minus root 3. So you integrate from negative root 3 up to positive root 3, the thing that you get for arc length, which is the square root of dy dt squared plus dx dt squared. That will eventually, just through doing a bunch of algebra, simplify to this. And then you can use that symmetry argument if you want here. You don't have to, but it saves a little time. And the antiderivative is not hard. So there's a few things here that are tricky. Finding what the graph looks like, seeing where the loop starts and ends, finding the t values, and then all the algebra that was required to get us to that integral. There was some slightly tricky algebra there, but not impossibly difficult. Right? You just factor out the 12, then FOIL everything out, combine your like terms. Once you get here, you factor this, and that square will cancel with the square root. All right, I do have to get running. Today is a bit of a busy day for me, so if you guys want to talk more, come see me in office hours. Otherwise, send me a message on Canvas. I will be doing one extra office hour over the weekend to try and help prep people for the final. So try to come to at least one office hour between now and the final. I highly suggest it. And when it comes to exam 3, just make sure you go back and spend some time reacquainting yourselves with power series. Don't let power series be your downfall here. So go back, practice the power series stuff. Solve those study guide problems honestly and earnestly. I'll go in once tonight to look for anybody who's submitted any study guide stuff. Remember, you can submit it half done. You can submit just the problems you want feedback on. Submit whatever you want. I'll go in tonight to look and give feedback on those. I'll go in one more time tomorrow to look and give feedback on those. And then your exam 3 is Friday during class time, and it will cover the materials that we mentioned in that list. I gotta get running. I'll see you guys. Oh shit, I won't see you guys again. This was our last class, wasn't it? Oh damn. Well, if I don't see you in office hours, then I hope that you have a lovely holiday break. Please don't forget to register for classes in the spring. I know this is not something that you guys are concerned about, but Santa Fe's enrollment is way, way down. COVID makes things rough. We all acknowledge that. But the college is in need of your support. So the sooner you can register, the more helpful that will be for our budgets, letting us know if you're going to come back and take classes in the spring. So don't forget to register. And if you need help or if you want to talk to me, if there's anything at all I can do for you, please reach out. Remember, if you're paranoid about grades, if you're thinking about dropping, if there's anything like that, I can help you, but only until 5 p.m. on Friday. That is the last time I am able to do anything registration-wise for you. So if there's any conversations like that that you want to have, make sure you have them with me before 5 p.m. on Friday.
Can I ask one quick question?
Yes, yeah.
Do we have to show the work for anything that's not going to be on exam 3 on the study guide?
I want to see whatever work you would write down to solve the problem. All right, so just go ahead and you don't have to like polish it up or rewrite it or anything. Just scan for me the actual work you wrote down solving the problems, and that will be fine.
Okay.
All right, take care, guys.